Hi, my name is Michael Collins. In this video I'm going to show you how you can take the output from Microlab's visual spectrometer as a digital photograph and incorporate it into the ImageJ software, which is available from the National Institute of Health as a free download, in order to produce intensity plots and do a wavelength calibration in Excel. So let's get started. First thing, when you open ImageJ, this is the main window that comes up. It's kind of a small window. It's got the usual menu bar and a bunch of tools that you can use. We're actually going to be using only this select tool, which is a rectangle that we can draw around the spectrum that we want to look at, and we're going to be using the analyze tool in order to do a plot profile. Let's start by opening the photograph. I have loaded onto my desktop an image that I took of a mercury lamp in front of the slit and a helium lamp in the through the fiber optic cable on the Microlab visual spectrometer. So down below here, this is the helium output, and up above we have the mercury output. Notice that there seem to be three main lines, but there are also, I don't know if you can see this, I hope you can, there are also very dim lines, and these are real. These aren't shadows or ghosts. These are actual lines, and you can go online and find the actual wavelengths of each of these. I have a spreadsheet program that I've developed that's available from Microlab. It's nothing special, but what it does is allow you to take the excuse me, the helium line positions in pixels and compare them to the known line positions in nanometers to prepare a helium wavelength calibration plot that relates pixels to wavelength. We also have the capability using what's called the linest or lineest function in Excel to carry out a fairly extensive linear least squares estimate of the best fit of the line in the calibration. And the advantage of this over just fitting a curve, which we'll also do, is that it puts the slope and the intercept into cells that you can reference down here when we want to create the actual intensity versus wavelength spectra. Okay, so we're going to be doing the calibration. We're going to be measuring the mercury lamp pixels, and from the calibration plot we can convert that into wavelengths, and we can carry out a comparison of our calibration line values with the known lines for mercury. So let's get started. The tool that we're going to use is a selection tool, and I'm going to start by drawing a rectangle, and I'm going to basically capture the entire screen left to right and kind of rope all of the lines from the helium tube, and then we're going to do an analyze in which we measure the plot profile. And here we are. So what we have now is a relationship between the pixel position left to right and the intensity of the spectral lines from the helium lamp. So here we have, again, going from the violet line through to the aquamarine line. The aquamarine line shows up out around 668 pixels. Again, if you look at this as I position the cursor, you can see the pixels down below, and you can see the pixels show up above in the ImageJ main window. Then we'll go all the way out to the red, okay, and that's going to capture the pixels in the window, and it's also going to capture the pixels in the plot. So here we have it. Let's go back to Excel after we get these, and I'm going to just quickly, this one shows up at around 299, about 368, $4.99. We're starting down the violet end. 299, 368, and $4.99. Excuse me. Let's go back to this. 614, 672, 1148. I'll go back and get that last one. So again, 614, 672, 1148, and 1602. Now notice when I put this last one in, the LinNest results will populate, and we completed the calibration curve. So we have a slope relating pixels to wavelengths of 0.1776. That is 0.1776 nanometers per pixel. So if you're off by a couple of pixels here, it really doesn't matter when it comes to the wavelength accuracy, because you're still within the resolution of the grating in the slit. We also have a little more significant figures over here in our LinNest output. Okay, let's go back now and finish this helium thing. I want to show you one more feature of the ImageJ window. We can click on list and get a list of all of the distance in pixels and intensity values. We can also copy. I'm just going to click on copy, and then we're going to go back to the Excel. I'm going to go to the top of the column where we're going to put this in, and we're just going to hit paste. And notice what happens is when I do that, I get all the data from the ImageJ window populating the first two columns from cell A22, and we're using the results of our calibration curve in order to convert the pixels into wavelengths, and I've created a wavelength versus relative intensity plot that basically replicates what we've got in the pixel count. So this is essentially the exact same rendering, but now we've done the calibration and we've got it in wavelength, not in pixels. That's pretty cool. We're going to do the same thing now with the mercury line, except instead of using the mercury for calibration, we're going to actually take the mercury lines and populate this area, and we'll be able to convert pixels from the calibration curve into wavelengths and compare those with the most intense lines, wavelength values from the literature. So again, let's go back to the photograph, and now we have this rectangle. I'm going to select it. I'm going to use the up arrow to move the rectangle up and capture the mercury line. And to save time, I'm just going to go up here to where we are completely within. I'm not going to center it. And now we're going to go to the ImageJ software, and we're going to get a plot profile. Alright, here we have it. And again, we have the less intense lines showing up. So we have a bunch of lines out here. These are showing up as low intensity lines. We have other lines, again, low intensity, but they're showing up as little spikes. I'm going to actually make this big, and you can see out here around 1200 pixels. This appears to be, and actually is, a close doublet. So I'm going to pick the pixels here, and again, let's take a look. 303, 922, 1095, and 1110. 303, 922, 1095, and 1110. 303, 902, 1095, and 1110. Okay, so let's take a look here then. We've got our pixels converted to wavelengths. Alright, and compared that with the known, we seem to be off by about 1.2 nanometers. 902. Let me go back and make sure I got that one right. Is it really 902? 918, I'm sorry, I messed that one up. Let's go back here, 918. Alright, that's much closer. So we've got now our wavelengths. We really have all the information we need. But I want to show you one more feature. We can go back here, and again, as before, we can copy. And going into the first row that's available, we can paste. And we can generate the plot in the mercury spectrum. Whoops. Try this and try it again. There. The mercury lamp spectrum output, but now we have it in wavelengths, in nanometers. So, again, as you can tell, just from looking at this, we have an excellent correlation between the pixel count and the wavelength. So we have a real good calibration curve with lots of degrees of freedom. And by comparing the pixel count in the mercury lamp and the wavelengths generated from the calibration curve with those from the literature, we can see just how close we are. And it looks like we're within about a nanometer to a nanometer and a half in terms of accuracy. So there you have it. You can do this for any lamp that you want. Some have more lines, but again, I like the helium line because it has 7 well-known wavelengths that span the entire spectrum, and so you get calibration covering virtually the entire visual range. In the next video, we'll be looking at absorbance and how you can get absorbance spectrum quantitatively